February 11, 1986. The Rogers Commission is investigating the Space Shuttle Challenger disaster. A room full of engineers, executives, and officials have been talking for hours. Then Richard Feynman, 67 years old and dying of kidney cancer, picks up a piece of O-ring rubber, a small clamp, and a glass of ice water. He clamps the rubber, drops it in the water, and holds it there for a few seconds. He removes it. The rubber has lost its elasticity. He shows this to the cameras. He says nothing further. In 5 seconds, using a glass of ice water and a piece of rubber, he explained the cause of a disaster that killed 7 people and that had been obscured by institutional language for weeks. That was Richard Feynman, a theoretical physicist who could talk directly to reality in a way almost nobody else has managed before or since. This is Feynman in 10 minutes. Richard Phillips Feynman was born on May 11, 1918, in Far Rockaway, Queens, New York. His father, Melville, was a uniformed salesman who raised Richard to question everything, to look at the world as a set of puzzles to be solved, and to trust observation over authority. As a child, Feynman repaired radios in the neighborhood by thinking through how they worked rather than following manuals. He taught himself calculus and trigonometry before high school. He entered MIT, then Princeton, where he completed his PhD in 1942 at the age of 24. He was immediately recruited to the Manhattan Project at Los Alamos. He was 24, surrounded by the greatest physicists in the world, and he spent part of his time cracking safes for amusement and driving the security officers insane. He was irreverent, relentlessly curious, and genuinely indifferent to rank. He corresponded with his wife Arlene, who was dying of tuberculosis in a hospital nearby, writing her coded letters to frustrate the censors. She died in June 1945, 5 weeks before the first nuclear test. Feynman was present at the Trinity test on July 16, 1945. Everyone else put on protective glasses. Feynman reasoned that the windshield of the truck he was sitting in would block ultraviolet radiation, so he watched the detonation with his naked eyes. He was the only person who saw the first nuclear explosion without filters. He watched it turn the sky white, then orange, then the mushroom cloud rose. He said afterwards that he felt very peculiar. He was the only person thinking about the physics of the explosion. Everyone else was just watching. After the war, Feynman worked at Cornell and then at Caltech, where he spent the rest of his career. In the late 1940s, he developed what became the defining work of his scientific life, a complete reformulation of quantum electrodynamics, the theory describing how light and matter interact at the quantum level. Quantum electrodynamics, QED, had existed in incomplete form since the 1920s, but its calculations kept producing infinities, meaningless results where finite numbers were expected. 3 physicists solved this independently in the late 1940s: Julian Schwinger, Shinichiro Tominaga, and Feynman. All 3 reached the same answers through completely different mathematical approaches. Feynman's approach came with a tool that nobody else had thought of: diagrams. Feynman diagrams are simple pictures representing the interactions between particles. Lines represent particles. Vertices, where lines meet, represent interactions. A photon being absorbed by an electron is a diagram with 2 particle lines meeting a wavy photon line at a vertex. Each diagram is a direct visual encoding of a specific mathematical term in the calculation, not decoration, not metaphor. Each diagram corresponds to a specific mathematical contribution. Add up all the relevant diagrams, and you get the probability of the interaction. These diagrams transformed how physicists think and communicate. Before Feynman diagrams, calculating particle interactions required pages of obscure mathematical notation. With Feynman diagrams, the calculation could be laid out visually, checked for completeness, and shared between physicists who might be using different notations. Feynman diagrams are used in particle physics to this day, in every textbook, in every paper involving quantum field theory. They are one of the most practically useful theoretical tools ever invented. Feynman, Schwinger, and Tominaga shared the 1965 Nobel Prize in Physics for this work. Feynman later said he thought the prize was a nuisance because it made him famous and people kept interrupting him. But Feynman's greatest contribution to physics may not be the Nobel work. It may be the way he thought about explanation. Feynman believed that if you cannot explain something simply, you do not understand it. Not as a slogan, but as a diagnostic tool. When he could not explain something simply, he took it as evidence that his own understanding had a gap, not that the subject was inherently too complex. He would work on the explanation until it was simple, and in doing so, he would deepen his understanding of the thing itself. He applied this to everything. His Caltech lectures on physics, delivered to first-year students in 1961 and 1962, are still in print and still widely read by professional physicists who find insights in them. His BBC interview series, Fun to Imagine, recorded in 1983, shows him explaining everyday phenomena in plain English to a non-scientist interviewer. He does not simplify dishonestly. He simplifies by finding the right level, the layer of description that illuminates without distorting. 3 examples. Heat. Most people know that heat is related to molecular motion. Feynman made this concrete. He said all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. If something is hot, the atoms are jiggling fast. Cold means jiggling slowly. When you touch a hot surface, the fast jiggling atoms in the surface knock your slow jiggling atoms faster. That is all heat transfer is. Atoms bumping into each other and exchanging motion. Fire is jiggling that spreads from atom to atom in an unstoppable chain reaction. The sun is jiggling so intense that atomic nuclei fuse together and release the energy that holds them apart. All of thermodynamics is just atoms jiggling at different speeds. Rubber bands? A rubber band is a polymer, a long chain of molecules folded and tangled randomly. When you stretch it, you force those chains to straighten out and align. When you let go, entropy, the universe's tendency toward disorder, pulls the chains back into their tangled state, which is one of an enormous number of possible arrangements. The rubber band snaps back not because of any special force, but because the tangled state has far more possible arrangements than a stretched state, so any random motion will tend to return it there. That is why a rubber band warms when you stretch it and cools when you let it snap. Stretching reduces entropy, and entropy reduction releases heat. Feynman could take a rubber band and turn it into a lesson about thermodynamics, polymer physics, and entropy in 3 minutes. Magnets. When someone once asked Feynman why magnets repel each other, his answer lasted several minutes and ended with a refusal to give a simple answer. Because he wanted to explain why every simple answer requires understanding the deeper layer beneath it. Why do 2 north poles push apart? Because the electromagnetic force acts that way. Why does it act that way? Because of the exchange of photons. Why does photon exchange cause repulsion? Because of quantum mechanics. Why does quantum mechanics work this way? Nobody knows. The questioner wanted an analogy to rubber bands or springs. Feynman pointed out that every analogy is just a claim that one thing behaves like another, and at some level, that chain of analogies has to stop. Real explanation, he said, means identifying which layer of the hierarchy actually answers the question. Back to the ice water. On the morning of January 28, 1986, the temperature at Kennedy Space Center was 29 degrees Fahrenheit. Engineers at Morton Thiokol, which manufactured the solid rocket boosters, had warned overnight that the O-ring seals in the boosters had never been tested below 53 degrees and might not perform correctly. Their warnings were overruled. Challenger launched, the O-rings failed, hot gas burned through the joint, and the shuttle broke apart 73 seconds into flight. By the time the Rogers Commission convened weeks later, the institutional accounts had become tangled in technical language and bureaucratic framing. Feynman's ice water demonstration cut through all of it in 5 seconds. The material got stiff in the cold. The O-rings could not seal. The shuttle was launched anyway. Here is the experiment. You can do it yourself. After the demonstration, Feynman wrote his own appendix to the commission report because the official report had softened his conclusions. He wrote, "For a successful technology, reality must take precedence over public relations, for nature cannot be fooled." He died of kidney cancer 2 years later, on February 15, 1988. He was 69. His last words, according to those in the room, were, "I'd hate to die twice. It's so boring." Thousands of physicists who have never met him have been shaped by his lectures, his books, his diagrams, and his belief that the universe is not too complicated to understand. Only too complicated to understand if you are willing to stop at the first explanation that sounds satisfying. Feynman never stopped, and that as much as the Nobel Prize is what made him impossible to ignore,